Okay, good afternoon, everyone. Let's get started. So in the last lecture, we introduced the concept called expectation, right? So the intuition is that if you look into some random variable, right? Underlying random variable that represents some kind of like random phenomenon, random experiments you want to observe, obviously, um, the value of the random variable will have the chance to change, right? So it's not like some fixed value. And perhaps like when you observe the random phenomena, right? And in the first observation, you might say some value. And in second observation, you say a different value. Like you roll a die, right? This time you say 0.6. Next time you probably just say 2, right? So a natural motivation would be, okay, no matter I mean, although I can't control like, or I can't predict what's the likely the value you could say from the random variable, but I would like to say, okay, on average, what does this value look like? So that leads to the definition of the expectation, right? So on average, for example, you flip the coin, right? You say like you throw the coin for 10 times, like you say heads for 6 times and tails for 4 times, right? And keep doing that, and you see on average the value say like which are either 1 or 0 on average will be like 0.55 or 0.52, right? So that gives you a sense that, okay, on average, what's the behavior of the random variable's value, which reflect what's the underlying uncertainty pattern of the experiments, right? That's the motivation and intuition of the expectation. So basically, we have the definition for the expectation for 2 types of random variables. The first one is for discrete random variable. So discrete random variable, meaning that your sample space is discrete, right? It might be, say, 1, 2, 3, and you're gonna map each value to a real number, right? And there is this mapped value are discrete as well. And be careful, it discrete doesn't mean like it is finite. It could be infinite as well, right? We mentioned that before. For example, using the geometric distribution as example, right? The value of the random variable indicates, okay, if you do independent experiments, what is the first, at which experiment you're gonna receive your first success, right? If you guys have all finished homework 2, right? Homework 3, right? For the last problem, right, you have some crazy toasting machines, right? And you want to know, okay, after which bread, after baking, how many breads would it make your machine broken, right? So the number of breads are definitely integers, right? 1, 2, 3, 4, 5, but the possible range is infinite, right? Discrete just means that, okay, the value range of those random variables are discrete. So under this case, if we want to compute the expectation, it's simply the weighted average of those discrete values your random variable can take. And what's the weight? What's the weight? Any thought? Yes, the probability. The probability is weight, right? So you can imagine, like, let me write down first the formula, right? So for the discrete random variable, it is just a weighted average of all the values that random variable can take. The weight itself is the probability the random variable takes that value. That's it, right? So from this formula, you can say the higher probability the random variable takes some value, the larger the weight of that value are used in calculating the expectation, right? So it's like, okay, if you flip a coin, 1 is head, 0 is tail. Like if you have like 0.9 chance to see the heads, right? So then in your expectation, the expectation will bias toward 1, right? Okay. So this is the definition for discrete random variable. And for continuous random variable, because the value range, both the sample space and the value range are continuous. So you have a probability density function that characterize this random variable, right? So remember the definition of a probability density function. It just give you the way to calculate the probability that your random variable falls in any interval, right? So the calculation is an integration of the PDF over the range, right? So if we want to define an expectation for the expectation for a continuous random variable, we need to extend this discrete summation to continuous integration, right? So we're gonna integrate x multiplying with the probability density function, right, over the whole range the random variable's value can take. That's the definition for the continuous random variable. Does it make sense? Any questions so far? Yeah, we just give a quick review of what we have talked about on Tuesday, right? And this is a very, very important and fundamental concept. I hope everyone will, memorize it, not just through it in some dictionary, and when you use it, just open the book. And this is very, very fundamental, because we never, like, in the future, if you're doing your statistic job, or if you're doing your research work or whatever, right? Whenever you talk about some random variables, you first think about, okay, what is the expectation, and what is the variance? Variance is something we're going to concentrate today. Okay, so and then we introduced several examples for the expectation, right? Especially for the continuous random variable. We're now gonna repeat our calculation done on Tuesday, right? So for example, when we calculate the expectation for an exponential random variable, so the calculation is just a practice of this integration, right? Integrate x with the probability density function, and we use some kind of calculus 1 experience. We can get the expectation for a exponential distribution random variable is 1 over lambda. Lambda is the parameter of the distribution. Another well-known example is the Gaussian distribution, or the normal distribution, right? So the interesting thing is that the expectation for a Gaussian distribution is exactly this parameter mu. So remember, the Gaussian distribution is parameterized by two parameters, right? One is called mu, one is called sigma square, right? If we write down the PDF for a Gaussian distribution, it will be look like this. Right? So you can see that the whole PDF is determined by this mu and sigma square, right? And different mu and sigma square will lead you to different versions of this PDF, right? So this mu is called the mean parameter, and sigma square is called the variance parameter. Why? Because if you do calculation of the expectation under this PDF, the expectation is exactly mu. Okay. So if you do calculation, remember we're following the definition, right? The expectation of x, a Gaussian random variable, is the integration of x times this little bit lengthy exponential like term function, right? If you do this, and it gives you exactly mu. Right? Again, we recommend you to verify this by yourself. It is all the calculation is within the scope of calculus 1. Right? Although the calculation might be tedious, but you will see, surprisingly, the result is just right mu. That's why when people talk about the Gaussian distribution, they will ask you, what is the mean parameter? What is the variance parameter? And for this variance parameter, we'll say shortly, if you calculate the variance of the random variable x under this PDF, it will exactly sigma square here. Okay. So then at the end of the last lecture, we introduced a very, very important property about expectation. It's called linearity. So linearity, what does linearity mean? It just means like if you do a linear combination of the random variables, then take expectation. It's the same as you first do the expectation over every random variable and then do a linear combination. Okay. So the proof is very simple, but we'll postpone it because we need to introduce what does it mean for marginal probabilities. So right now we just use it as a fact. Right. So another thing which is directly from the linearity of expectation is that if you take an expectation of a constant value, what's that? What's that? Yeah, just constant value itself. Right? So expectation of a constant is just the constant itself. Why? Because it doesn't have any other values that can take. Okay, so then we can use the linearity of the expectation to simplify the calculation in many scenarios, right? I'm gonna skip this sum of dice rolls, right? I want to look at this very classical example to illustrate how useful this linearity of the expectation is, right? So we consider a random variable that follows a binomial distribution. So binomial distribution talks about if I repeat a binomial experiment, a Bernoulli experiment for multiple times, and how many successes can we observe? The Bernoulli experiment just like flipping the coin, toss a coin. If you see heads, you got success. If you see tail, you got failure, right? And it's suppose like you just independently do this Bernoulli experiments for n times. Then we would like to say, okay, how many total successes can we observe? this is what a random variable of binomial distribution means. So from our previous discussion, right? Remember we used nearly like half a class to talk about how do we derive the probability mass function for this distribution, right? So if we want to know what is the probability that a binomial random variable takes a value k, right? So imagine you're doing n of palm flipping experiment, right? And from this n outcomes, you say k has up. What's the probability? You need to count from how many in this n in this sequence of n outcomes, right? At which positions you're gonna say has up, right? So you need to consider a factorial, right? Which is it's not factorial, it's a combination number. Choose k from n. And then for each such sequence, the probability is 1 minus p n minus k, right? Because you failed n minus k times, and then you succeeded for k times. So that's the probability a binomial random variable takes a particular value k. Right? Everyone's comfortable? We're just repeating what we have discussed previously. I mean, if you feel like it sounds like not that familiar, that's fine. Just open our previous lecture slides and review it. Right? So, and here the k can varies from 1, 2, until n, right? Means that you can, oh, sorry, and I also miss k equals to 0, right? Right. Meaning that, okay, throughout these n experiments, you probably succeeded for 0 times, right? All failed. Every experiment failed. Or you succeed for 1 times, or succeed for 2 times, until you succeed until in the other extreme, you succeed in every trial. Like, any questions so far? Okay, and then follow the definition if we want to compute the expectation of x. What shall we do? Any thought? I mean, just using the definition. Mm-hmm. Mm-hmm. So just a weighted summation of all values k can take, right? X can take. So as we mentioned, all the values x can take will be 0, 1, up to n, right? And for each value x can take, we need to multiply the probability it takes that value, right? So if you write it down, it will be k from 0 to n, k times this hateful term, right? Seems not easy to address this, right? It's pretty, it looks pretty hard, right? To calculate this, right? So the good thing is that we can totally sidestep this issue. We're not gonna use the original definition to calculate the expectation of X. We're going to use the linearity of the expectation. We're going to do that, right? So like consider you toss a coin for n times, right? That's the n Bernoulli experiments, right? Each outcome are denoted as x1, so x1, x2, until xn. So each outcome will be either 1 or 0, right? For example, x1 might be 1, x2 might be 0, x3 may be 1, until xn may be 0, right? And then x, which is this binomial random variable, essentially is the total number of successes. That's total number of ones across this n outcomes, right? So x can be written as just the summation of n outcomes. Does it make sense, right? I mean, failure just means 0, right? And it adds up all outcomes all together, the summation will be the total number of ones, namely successes. Right? Does it make sense? And then let us look at the structure, right? You know, X is a linear combination of x1 through xn, right? Of course, it's a very simple linear combination, right? So according to the linearity, the expectation x is equal to the expectation of the summation, right? And it is equal to first do the expectation over every Bernoulli experiment's outcome, right? And then do the summation. And what's the expectation of each individual Bernoulli experiment's outcome? B times what? Mm-hmm. Mm-hmm. Yeah, this is the way to calculate the expectation of X in a standard way, right? In the original definition. Yeah, but here we want to leverage the structure of X, right? We want to use the linearity of the expectation. The relationship we'll find between X and every Bernoulli experiment's outcome is addition, right? X, which is the total number of ones, is actually the summation of x1 plus x2, x3 until xn. Right? Why? Because each Bernoulli experiment, its outcome is either 1 or 0, right? You want to know how many ones are in total out of these n variables, you just need to add them together. Right? And then we're going to leverage this relationship, right? Because this relationship will allow us to apply the linearity of expectation. Right? So expectation, linearity expectation, like as we mentioned, right? If you do a linear combination of the random variable, if you want to calculate the expectation of this linear combination, you just need to take expectation of each individual random variable and then linearly combine them. Right? So same thing here, right? So we know X is the summation of all the individual outcomes, right? X1 plus X2 throughout to Xn, right? So if you want to take expectation over this whole summation, it is equivalent to first calculating expectation for each individual outcome and then add them together, right? Now the question is that what is the expectation for each individual Bernoulli experiment's outcome? It's just P, right? Remember, this is a this is a result we have showing in the last lecture, right? For a Bernoulli random variable, meaning that you got probability P to take the value 1 and 1 minus P to take the value 0. The expectation is P. This is directly calculated from the definition, nothing strange. Question? Yes, P is the parameter which determines this probability. Other question? Okay, great. Then remember we are doing the Bernoulli experiment, right? Every Bernoulli experiment are parameterized by P. That means every Bernoulli experiment's outcome has the expectation P, right? So you basically you're gonna add P for n times. So eventually you add them together, you get your expectation of X, which is n times P. And that's it. That's the idea. It's very smart idea. If you can, I mean, you can do some hardcore calculation from this one. It will give you, sorry. It will give you NP for sure. Okay, any questions so far? Yeah, this is a very well-known example to show how useful the linearity of expectation is. Right? It's off. Yeah, and the next time, like whenever you're asked to analyze some like a binomial distribution, don't forget this formula. How do we efficiently calculate the expectation for a binomial random variable? Okay, so now I want to extend the expectation for random variable to for a function of random variable. I see I have a random variable X, right? Then I map X through a functions like G. This G of X will be another random variable. Question is that what is the expectation of G of X? Right? So I got X is a random variable, right? I got another random variable Y, which is a function of X. Then how do we compute the expectation of Y? Yeah, one straightforward way, I mean, one naive way is to calculate the PDF or probability mass function for Y first, right? And then apply the definition, right? Integration, sorry, the integration of Y times the probability density of Y, right? That's just follows the original definition. But here, we can also calculate the expectation of Y in another way. So we don't need to explicitly compute the PDF or PMF for this new random variable Y. We just need to do a weighted summation over the value that you apply G over X. What does it mean? Suppose X is a discrete random variable, and X can take values like A1, A2, A3, and so on, right? Then I'm gonna do the weighted summation over the values of G apply to every value AI X takes, and then weighted by the probability X takes AI. Does it make sense? Right? And then do it, right? You don't need to explicitly compute what is the probability density for or probability mass function for g of x. And similarly, when you have a continuous random variable, and then you map this continuous random variables through g, right? You want to compute what is the expectation of g of x. You only need to change the expectation formula, I mean the integration here, right? By replacing x with g of x. And that's it. Okay, any question regarding the definition? Everyone's comfortable? Okay, so yeah, to repeat, right? So if you have a function g over some random variable x, you want to compute the expectation of g of x, right? And the calculation is the same as you calculate the expectation of x, except that you're going to replace either in integration or in the summation, the value of x by applying g over the value of x. And that's it. Okay. So next, we need to introduce another concept called variance. So the expectation and the variance are kind of like two most important properties for a random variable. Is always will be the first-hand information you want to learn about a random variable. Okay. So what does variance mean? Intuitively, the variance just indicates how spread out your random variables can take, right? So you can imagine a random variable, if it is very concentrated on something, right? So the value could be taking a very small range. So let me draw it better way, right? So you have a random variable x, right? So you might have this -1, 0, 1, right? So for some setting of this random variable x, right? You might imagine, okay, if you look at the x value, right? If you just keep looking into the random phenomenon on the line x or doing some random experiments, right? You might say, okay, the values of x you observe is very, very centered around 0. It's just a little bit perturbation surrounding 0. And then you can imagine the spread of x's values are, on average, you say is small, right? On the other hand, for some other random variables, you might see, okay, this time you might see value here, this time you see here, this time here, see it here, right? If you do a lot of experiments, you can see, okay, the values actually take kind of like across a very large span. This indicates, okay, the values of this random variable, the distribution of this random is quite spread out. So we want to know that for a random variable x, how spread out its distribution is. To measure this kind of like spreading or spanning, right, we introduce this concept called variance. Does it make sense? Like give a more concrete case, like the temperature here, right? Temperature in Utah, as compared with the temperature in, I don't know, maybe in some like very hot Sahara desert. The temperature in Utah obviously has much more spreading than the temperature in Sahara desert, right? Like Sahara desert, okay, okay, it is constantly like surrounding at a very high range, right? Very high value, right? But in Utah, okay, in the summer it could be very, very hot, right? It could be like as high as I don't know, 100 degree Fahrenheit, right? And in the winter, it may be like a 25, right? So it's quite spreading out, right? But if you look at temperature as some like a um, desert, or I mean, yeah, in some country, like you always see it is very narrow. Or if you look at temperature at South Pole, right, it's always like throughout a year it will be very, very low, right? It's the I don't know. I don't know what's the range of what's the temperature in South Pole, but I bet it will be much more concentrated than the temperature in Salt Lake City, right? Okay, so that's why people introduced this concept called variance, used to measure the spanning or the spreading of a random variables distribution, right? So what's the definition? So the definition actually is another expectation. Or we can view it as a particular function of the random variable x, right? So we calculate the difference between x and its expectation and take the square. And remember, this guy is a function of x, right? And then we want to look at the expectation of this function. So this is defined as the variance. Like from the math formula, you see, okay, the square difference between the square of the difference between x and the expectation indicates how far away x's value can be taken away from its expectation, right? And of course, the value of x taken is random, right? So this time this difference might be smaller than this time. Next time, the difference might be quite large, right? Then we take expectation, want to see on average how far away x's value will be different from the expectation. That's how this variance definition is motivated. Okay, any question regarding the definition here? Everyone's good? Okay. So the variance is, you see, it actually takes a different skew, right? It takes the square of the difference between x and the expectation. Sometimes like people feel, okay, this might be a little bit uncomfortable because when you look at x's value, right, it might be like 0.5, 0.8, 1, right? And the expectation might be 0.55, right? And now I want to look at this variance. Actually, it is the difference between x and expectation of x and take the square, right? So kind of like takes a quadratic value level over the original skew of x. So it's not, that doesn't sound very comfortable. So then people propose another metric called the standard deviation, right? To force this spreading out measurement to be on the same unit as the original random variables value. So what is standard deviation? You just need to take the square root of the variance, and that's it. Okay. So the variance itself, like, okay, I'm gonna take expectation over the square, right? Now I take a square root. Of course, your unit comes back, return to the original skew. Yeah, that's the standard deviation. Okay, yeah, let's rest for 5 minutes and then I'll continue. Okay. Let's continue. So we introduced the standard deviation, which is just take a square root of the variance. Doing this can kind of like enforce our measurement of the spreading out for random variable takes the same skew or units as expectation of x, right? So from the visual effect, we can imagine, okay, so suppose this is x-axis, right? This axis are the range where the values x can take, right? Where indicate the value x can take, right? So this is the expectation. Right? So you can imagine x can take a variety of different values surrounding expectation of x. So when you use the standard deviation, you can use the standard deviation to locate a range which is centered around at the expectation. This range actually specify what's the most frequently observed values for x. Does it make sense? Right? We're gonna relook at this interval again because it will relate to the hypothesis testing and the confidence intervals when we're gonna discuss them in the later stage of this semester. Okay? But here just give you a sense why the standard deviation is so useful, because it directly tells you, okay, how does the span of the distribution of x look like, right? So that's why people often like use standard deviation to construct the radius of a range for which the most common values around the variable can be observed. Okay. So now, I mean, again, let's see several concrete examples to practice the understanding of the definition. Right? So first, Bernoulli random variable again. Right? So when we say x follows a Bernoulli distribution, it just means x can take value as a 0 or 1. And we have the probability mass function like this, right? X equals to 1 is P, and X equals to 0 is 1 minus P. Okay, so then the conclusion is the variance of a Bernoulli variable is P times 1 minus P. Remember, the expectation is P, right? Now, when we calculate the variance, the result is P times 1 minus P. Why is that? Right? We can just verify it through the definition. So the variance is defined. Look at this right here. The expectation of the square the difference between x and its expectation, right? So just use this. So it is expectation squared of x minus the expectation of x. What is the expectation of x? It's just P, right? Right. How do we calculate this expectation? Right. Use what we just discussed. How do we calculate this expectation? How do we calculate expectation of square of x minus P? Yeah, we have replaced the expectation of x with P already. Right? The variance is defined as the the square of the difference between x and its expectation, right? And here E of x we know is p, right? So now the task is to compute the expectation of square of x minus p. Mm-hmm. Yeah, definitely, right? Definitely. Okay, I'm gonna use the very naive approach first, and then using your, you know, um, expanding this square term and do the linearity. I'm gonna try both. Right? So the first one, remember this guy is a function of x, right? This is square of x minus p, right? X minus p squared. It's a function of x for sure. And if you want to compute a function of random variable, how do we do that? We just do a weighted summation, right? A weighted summation over the function of every value x can take. It's ai, then times the probability x take ai, right? This is the same as the expectation for random variable, except that, okay, you're gonna do a weighted average not over ai rather than g of ai. Does it make sense? Yeah, okay. And then let's just do it, right? It's just quite mechanical. So we know x can only take two possible values, right? So that means when x takes 0, this guy becomes 1, 0 minus p squared. And what's the probability of x takes 0? It's 1 minus p, right? So, and then plus, when x equals to 1, then this g of x will be 1 minus p squared, right? And what's the probability x take 1? Just p, right? So now you just add them together. If you do this, you will get p times 1 minus p. Does it make sense? Yeah, again, this is a good practice. We recommend you guys to to replicate this after class, right? So another way of doing this is that, okay, I'm gonna look at, okay, this is a square difference, right? So this square difference can be expanded as x squared minus 2x times p plus p squared, right? This is a quadratic form, right? And then I can use linearity of expectation, right? Expectation of x squared subtracted by 2 times the expectation of x times p plus p squared, right? It's just the linearity of expectation. And this guy is 2 times p, right? Expectation of x is p and times p. And this guy is p squared, right? And this guy you need to calculate by yourself. It's just x squared. And what's the expectation of x squared? What's that? Can anyone just quickly calculate for me? Yes. What's that? Yeah, I'm asking what's the expectation of x squared? What's the expectation of the square of x? I'm not pulling out square. What's that? Yes. It's like brain teaser. It's just a P. Why? I mean, just you just apply it, right? So x squared, right? X squared, when x equals to 0, x squared will be 0, right? You times minus P plus when x is 1, x squared will also be 1, right? So the calculation is exactly the same as you calculate the expectation of x. Right? Sorry, it's P here. So this will give you P. Right? So you see that, okay, this guy is P. This guy, now, well, this guy you need to subtract it by 2P squared plus P squared. It is just a P minus P squared. Right? This is here. Any questions so far? Yeah. Again, we recommend everyone to verify this and replicate this calculation because it's very helpful for you to understand the definition of the variance. Okay, so now I'll come to our old friends, right? Gaussian distribution again. So fx, the PDF of the Gaussian distribution will be something like this. X minus mu square, right? So if we want to calculate the expectation of the variance, it will be expectation of x minus mu square, right? Why it is this? Yes, exactly, right? I just want to remind everyone, okay, the expectation of x itself is mu. So the variance will be the expectation of square difference between x and mu, right? So this one, if you just calculate follow the definition, you're going to calculate this integral. It's very, very painful. It's still doable. I mean, if you want to do it, it is doable. And I recommend you to do that. I'm not going to do that because I did that many, many years ago. Right? So, but the result is sigma square. We just give you the result, which is just sigma square. Right? So that's why people call this sigma square as the variance parameter. Because if you use this form of the PDF, where your sigma square sit here, your mu sit here, you calculate the variance following the definition, the variance is exactly sigma square. This is a very, very well-known result, and hope everyone can memorize this. Okay, any question? Great. So from the there's an alternative definition of the variance, which is also like a very popular when you calculate the variance. So what is the alternative definition? By the way, this alternative definition is totally equivalent to the original definition. So the variance can also be computed as the difference between the expectation of x squared and the square of the expectation. You see the difference, right? In the first term, you're going to take the square of the x and then calculate expectation of x squared, right? So here x squared can be viewed as a special function of x, right? You're calculating an expectation of a function of x. But the second term, you just calculate the expectation of x and then take square. Okay. So there's no like function transformation of x. Right? You just calculate expectation of x and take square. So you see the square actually is outside of the expectation. In the first term, the square is inside the expectation. And the variance is the difference between these two terms. So any question regarding the definition? I hope no one is getting confused here. The key difference is where the square sits, right? The first term sits inside the expectation. The second square sits outside the expectation. Okay, then the question is why this is equivalent to the original definition of the variance. Okay. So let's do some practice, right? Throughout this practice, it helps us to further understand the properties of the expectation. So the original definition of the variance, as we discussed, is you take expectation of the square difference between x and its expectation, right? So that's the original definition. So to simplify this, right, to change this, we want to make some kind of like expansion, right? This is a quadratic term. So I'm gonna do some, I'm gonna take out all of this term. So you will have x squared subtracted by 2 times the cross term, right? Plus the square of the expectation of x. Everyone agrees with this, right? It's just a normal expansion of a quadratic term, right? So you see these 3 terms are just a linear combination, right? So you can use a linearity of the expectation. Okay. Meaning that we can first do expectation over each of these 3 terms and then combine them together. This is a linearity. So that means this expectation will be decomposed as expectation of x squared, right? Remember, x squared is now as a function of x. Then you take expectation and then plus expectation of, should use minus the expectation of ex times x, right? And plus the third term, we take expectation. The third term is the square of the expectation. Does it make sense? Right? So now let us look at the 3 term, right? So the first term, of course, it is the expectation of x squared. But the second term, what can we observe? You see expectation of x, e of x, is a constant, right? E of x is constant. It doesn't have any randomness, right? It's a constant factor, so you need to move out from an expectation, right? And the constant factor like 2 or 3, right? And multiply a random variable, you just need to move the random variable, move the constant factor out of the expectation, right? So now, for the second term, we can further simplify it as the expectation of ex, it is move out, right? And times the expectation over x only. Okay. Any question? Okay, so then let us look at the third term. The third term. How do we simplify the third term? Yes, exactly, right? That's a very, very important observation. Remember, E of x, Ex itself is a constant, right? You take a square of constant, still constant, right? So you take an expectation of constant is the constant itself. There's no need to put an expectation outside of it, right? So you can just remove the expectation in the outer side, right? In the outer, right? Which gives you square of expectation, right? That is the constant itself, right? So now let us look at the last two terms. What can we observe? Yes, right? So you can see the second term, essentially, this guy is a square of expectation as well, right? So you're gonna subtract by 2 times square of Ex, then plus Ex squared, right? You just combine them, you're gonna have a minus square of Ex. I'll put this guy here. This gives our alternative definition of the variance, right? Which is just the expectation of x squared subtracted by square of expectation. Yeah, hopefully you will practice this proof, because there are many proof in the statistical literature. They use the same trick. You do some expansion, use linearity of the expectation. You found out, okay, some cross term can combine with some square term over the expectation, and then you have some reduced form. This trick is applied everywhere in the statistics. Okay. Okay. So a very important property about variance is called scaling property. What does it mean, right? If I do a shift, meaning a linear shift or linear combination, a linear transform about around the variable x, like say I multiply x with a and then plus b. And then I take the variance. Then you need to take the coefficient a outside and take the square of a. So basically the variance of ax plus b equals to a squared times variance of x. So this is different from expectation, right? If I do expectation over this linear transform, it is a times expectation of x plus b, right? So this is a linearity, right? But for variance, there's no linearity. Instead, you're gonna square the coefficient that multiply x, and you remove the constant b. And why is that the case? This can be showing from the definition. Right? So let's do it so that we have like a better insight of this, right? The definition of variance, right? So we're gonna use the second definition. So we know the variance of X is the expectation of um, okay, let's use the first definition. Expectation of X subtracted by expectation of X and take square, right? The square difference of between X and its expectation. So now we consider X is now replaced by a linear transform of X. So the expectation of a linear transform of X is what? Just use linear to here, right? So you got A times expectation of X plus B, right? So now we subtract this AX plus B by its expectation. This will give you AX plus B subtracted by A times expectation of X plus B. So we see that B is canceled, right? So you are only leaving A times X minus E of X, right? And remember, this is just the difference between this linear transform and the expectation of linear transform. You need to take square. So that basically means after you take the square, after you take square, you have A square times X subtracted by EX square, right? Now I'm taking expectation, right? I'm taking expectation over this guy. You see, this is just a constant factor times another random variable, right? This X minus EX square is a random variable, right? You could just need to move the constant square, the constant factor out. Then you take the expectation only for the random variable itself, which is the square difference between X and EX, right? So what's this guy? What's this guy? Yeah, that's the variance of X, right? That's the definition. That's the variance of X. That's how we get here. The scaling property of the variance. That's why we have to take the square of the coefficient that multiplies with X. Okay, so let's stop here today, and I'll see you on next Tuesday. Thank you.